Welcome back, students. In this video segment, we will talk about one section today. In this section will be 2.7, graphs of the tangent, cotangent, cosecant, and secant functions. Now, let me tell you, the title of the section is long, but the lecture is very, very short compared to the amount of time we've taken to graph the sine and cosine function. The reason for that is that the sine and cosine function in the sciences play a huge role. The other trig functions, the other four trig functions, I've noticed don't play such a significant role. So with that in mind, what I'd like to do is I'd like to present you with the graphs of the remaining four trig functions, and that's it. I'd like you to, if you would remember or memorize one full period of each of the four trig functions, other trig functions besides the sine and cosine. And that's it for our course. Now in calculus, you're probably going to do work with all six of the trig functions and much more work with specifically the tangent, cotangent, cosecant, and secant functions. At that point, though, you will have developed some really fancy techniques for looking at graphs. So the idea is just to get a basic idea of the shape of each period of the remaining four trig functions. So let's go ahead and get started. The first trig function I'd like to address today, or in this video segment, is the tangent function. So let's take a look at y equals the tangent of x. Now the tangent of x has a problem, if you will, that the sine and cosine functions didn't have. The tangent function can be written as the quotient of the sine and cosine functions, and the problem here, or a potential problem, is that the cosine of x takes on the value of 0 sometimes. In fact, it takes on the value of zeros at an infinite number of places. So that's a problem in terms of getting a y value. Specifically, there is no y value on the tangent function wherever the cosine is 0. We cannot divide by 0. We simply can't divide by 0. So let's address that problem as we take a look at getting a nice image of the graph of the tangent function. So we can consider the tangent function as sine over cosine, and the first problem or point for the tangent function is where x equals, where is the cosine of x equals 0? Where is the first positive point at which the cosine equals 0? And that point is pi over 2. Okay, so what I'd like to do is maybe think about the tangent function the way a calculus student would. So don't worry about it. We're not going to need any calculus for this, but we are going to think about the tangent function the way a calculus student would. A calculus student would take note that x equals tangent of pi. I'm sorry, x equals pi over 2 is not allowed for the tangent function. It's not in the domain of the tangent function. So in calculus, what we would do is we would concern ourselves with what happens to the function or the graph of the function if we let x get close to that value. How close to that value? Infinitely close to that value. So if this is troubling for you, don't let it be too troubling for you. Let's just move forward with it. X equals pi over 2, according to my graphing calculator, is equal to 1.570796327, and that's where the graphing calculator stopped. But this value goes on and on and on. This value is representative of an irrational number. Pi is an irrational number. You can't write it as a fraction. So half of pi is also an irrational number. So this is the decimal representation of pi over 2. So what I'd like to do is let x get close to that value and see what happens with the graph of the tangent function. So let's construct a chart of values the way we did for our very first exposure with the sine function. And let's choose values that are getting progressively closer to that pi over 2. So Well, we need to start somewhere, so let's start with 0. 0 is pretty close to 1.57, etc. It's not that close, but in the scheme of things, it's pretty close. Well, the tangent of 0 is 0. So the tangent function goes through the origin. Let's let x get a little closer to pi over 2. Well, let's let x equal pi over 4. Pi over 4 is half of pi over 2. And then we're looking at the tangent of pi over 4. By now you probably have it memorized as it taking on the value of 1. So the point on the graph of the tangent function is pi over 4 comma 1. Well, pi over 4 is not that close to pi over 2. I want to get significantly closer to pi over 2. Like how much closer? Well, how about 1.5? 1.5 is fairly close to 1.5707, etc., etc. It's off by 0.0707, etc., etc., etc. So it's pretty close. Now, at this point, I'm going to rely on my calculator to give me the approximate values, and I'm going to round these values off to the nearest whole number so we don't have to deal with decimals for now. So if x equals 1.5, the y value is approximately 14. Okay, so what this is telling us right off is that the tangent function doesn't appear to have an amplitude, that highest point that the sine and cosine function have. Let's take a look at the graph of our points so far. So let me construct a set of axes. I'm going to do this. That's good. I can always modify it if I need to. So I'm letting x equal. If I let x equal 0, I get y equals 0. So let's put the points in a nice thick red. The origin. Well, we're not allowed to let x equal pi over 2. So what I'm going to do is I'm going to put pi over 2 right about here. And through x equals pi over 2, I'm going to draw a vertical line. Through x equals pi over 2, I'm going to draw a little vertical line. Okay. It'll be pretty clear. It'll become pretty clear why I'm drawing this little dotted line. And I'm trying to draw it really accurate here. Maybe too accurate, but that's okay. Okay, so there's x equals pi over 2. And I've drawn a dotted line there just for the time being to indicate that we cannot let x equal that value. That value is forbidden because the cosine would be 0. Then we'd have tangent of pi over 2 equals sine of pi over 2, which is 1, over cosine of pi over 2, which is 0, and 1 over 0 is not defined. So far we have the point 0, 0, and then if x equals pi over 4, right about there, we have y equals 1. Now I'm not going to make the y-axis exactly to the same scale, in fact not even close to the scale of the x-axis, so I'm going to put 1 about right here. So if x equals pi over 2, the y value is exactly 1. Now, if x equals 1.5, then the y value is 14. Well, pi over 2 is about 1.5707, etc., etc., etc. So I'm gonna put 1.5 about right here on the graph. That's really not close enough to pi over 2. The way I've drawn it, it should be much closer, but I'll take it for now. The y value is about 14. Remember, these are approximate values. It's really a decimal that goes on forever, but just so we can graph things in this video segment, I'm going to round off to the nearest whole number. Now this 14 may not be quite to scale. In fact, it should probably be higher, but I'll use that to represent approximately 14. So if x is 1.5, the y value is about 14. So the tangent function appears to be getting very large as x gets close to pi over 2. Well, how large? Does it stop getting large? Well, let's get closer. Let's do the thinking like a calculus student thing. Let's get closer, a little bit closer to pi over 4, or pi over 2. Let's take x to equal 1.57. Okay, so I'm letting x equal the first 2 decimal places of pi over 2. So I'm increasing the previous x value by a very little bit. The increase from 1.5 to 1.57 is by 7/100ths of a point. So I'm not making x that much bigger. Okay. However, the y value becomes disproportionately bigger than the previous y value. So the y value is about 1,256. So that's pretty startling. Well, let's keep this going. Let's let x get even closer to pi over 2. Let's let x equal the first 4 decimal places of pi over 2. Now I'm increasing x from 1.57 to 1.5707. So I'm increasing x by just 10,000ths of a unit. 0.00007 is added to the previous x value. So I'm adding a very, very little bit of an x value, but the y value doesn't increase correspondingly in a corresponding small amount. The y value is now about 10,381. Okay, so the y value is increased by not quite 10 times, but the previous y value, but by quite a lot. And this behavior just keeps going. In other words, the closer I get to pi over 2 as I creep in from the left, the larger the y values get. Okay, and this behavior is describing something that you studied not very much, but a little bit in intermediate algebra. It's called a vertical asymptote. As x gets very close to a specific number, the y values become infinite. We have something called a vertical asymptote, and that's what the tangent has at x equals pi over 2. So I'm going to keep the vertical line increase. I'm going to increase it by a little bit. Now I'm going to connect these dots. I'm going to connect these dots to get an image of the tangent function after I put the 3 points that I got in one of a kind of a solid red there. Okay, so here's the tangent function. Increases and increases and increases, and then it really shoots up. It really shoots up. In fact, the closer to pi over 2 that you get, the steeper the tangent becomes, giving us this vertical asymptote. So do you remember in intermediate algebra what functions gave you vertical asymptotes? Well, depending on your intermediate algebra instructor, they were the exponential functions, the logarithm functions, and some intermediate algebra courses, they cover conic sections like hyperbolas and stuff. So if you didn't cover the hyperbolas, that's okay, but you definitely studied logarithms and exponential functions. And the logarithm function has a vertical asymptote, just like the tangent does. Now, unlike the logarithm, however, the tangent function has more than one vertical asymptote. It has to, if you think about it. All the trig functions are periodic, so periodically they repeat all of their behavior. So if the tangent has one vertical asymptote, it has infinitely many. Okay, so let's take a look at the tangent function to the left of the y-axis. Now, to get the graph to the left of the y-axis is not going to be too rough. And the reason it's not going to be too rough is that the tangent function is an odd function. This may not be immediately clear to you what I'm talking about, but we'll give it a shot. So let me get a dotted line at negative pi over 2. See if I can do that. That's okay. The tangent of negative x, the tangent of a negative x value, is the opposite of the tangent of a positive x value. So if you replace x with negative x, the tangent gets replaced with negative tangent x. That means the y values are negative when x is negative. If you miss that, it's not that essential in this course that you associate odd functions, the odd trig functions, with their graphs yet. In pre-calc, it's a big deal, and it's a good thing. But right now, it suffices to say that we're going to get the same behavior to the left of the y-axis as we do to the right. And what you're looking at here, what you're looking at is one period. You're looking at one period of the tangent function, and you ought to memorize it. This is one period of y equals tangent x. Now, how do I know it's one period? How do I know it doesn't have more of a shape to a period? What's the distance between negative pi over 2 and positive pi over 2? The distance between those two asymptotes is pi, and that's the period of the tangent function. So you are looking at one period of the tangent function. Okay, so you ought to memorize that. You definitely ought to memorize that. In terms of detail, really at this point, I'm just hoping that you will memorize the basic behavior of the tangent function. So if I said sketch exactly one period of y equals tangent x, this is what I'm looking for. I'm going to put a little arrow on the ends of the graph to indicate that the graphs go up as x become infinite as x approaches pi over 2 from coming in from the left-hand side, and as x approaches negative pi over 2 from the right-hand side, the y values become negatively infinite. So I'll indicate that with the arrow on the end of the negative part. Now, this is one period. So if I wanted you to sketch two periods, we just continue this graph. Where would be the next asymptote? Where would be the next asymptote for this tangent function? Well, if the period is pi, then the next point where the tangent is 0 from the origin, the next point would be at pi away from that. The next asymptote would be pi away from pi over 2. So it would be at the previous asymptote plus pi more, or at the previous asymptote plus 2 pi over 2, or 3 pi over 2. 3 pi over 2. It's not coming out real well, okay? So if I were to ask you to sketch two periods, you would just copy that one period, and now you're looking at two periods graphed. Okay, so there's two periods of y equal tangent x. What I'd like you to do is, again, just memorize the shape of one period of the tangent function. In fact, I want to do that with the tangent, cotangent, secant, and cosecant functions. Okay, our next function, y equals cotangent of x. The cotangent also has a period of pi, and unlike the sine and cosine, remember the sine and cosine graphs are just shifted over from one another by pi over 2. Unlike sine and cosine, the tangent and cotangent function are not shifted over by pi over 2, but close to that idea. So what I'm going to do is I'm going to graph one period of the cotangent function. I'm not going to indicate any of the analysis that I gave for the asymptotes. In fact, I'm not going to do any kind of analysis like that for cosecant or secant as well. I want you to just memorize the graphs of these trig functions. The analysis will come later. The analysis of the asymptotes and such will come in a calculus class. So the tangent function, at least one period of the tangent function, let me highlight it in red here. One period of the tangent function takes on that shape that's indicated. It increases as we go from left to right. The cotangent decreases as we move from left to right and shifts over by pi over 2. So if you shift the tangent over by pi over 2 and then flip it upside down and reflect it about the x-axis, you'll get the graph of the cotangent function. So I'm gonna graph that for you now. So here's one period. This is one period of cotangent x. Y equals cotangent x. One period of y equals cotangent of x. Again, my recommendation for this course, just memorize the basic shape. Just memorize the basic shape. Now this video segment is promised to be really short. The only other thing I'd like to do is to take a look at the other two trig functions, the graphs of the secant and cosecant functions, and again, for those two graphs, I just want you to memorize the basic shape. Until you get to calculus where you do all kinds of analysis with graphs and stuff, I just want you to have the basic shapes of the non-sine and cosine functions. So let's take a look at, let's say, y equals, let's say, cosecant of x. Cosecant of x. Well, cosecant of x is 1 over sine of x. So just like the tangent and cotangent function, the cosecant and secant are going to have vertical asymptotes. The only really nicely behaved graphs in terms of no asymptotes are the sine and cosine. All the other trig functions have asymptotes. The cosecant will have asymptotes wherever the sine is 0. The sine is 0 when x equals 0 and pi and 2 pi. So at those values, we're going to get asymptotes. Okay, so let's do that. So in fact, what I think I'm going to do, besides graphing those asymptotes, I went off camera for a second. Besides graphing those asymptotes at 0, pi, and 2 pi, 0, I'm going to use a technique that was passed to me not by my trig teacher a billion years ago, but by some students of mine maybe 2.5 decades ago. There's a little trick for graphing the cosecant and secant functions. The trick is to graph the asymptotes as I've got them graphed for us at 0, pi, and 2 pi. At least those are asymptotes within one period. Then also graph the sine function. Cosecant is 1 over sine, but graph it dotted, and maybe even in a different color, but at least dotted. The dotted graph is not going to be part of our function, but it's going to allow us to get the graph of the function very, very nicely. Then the trick is this. Wherever we have an asymptote, imagine cutting the dotted graph, slicing it, cutting it as if it were a piece of string, So we're going to cut the sine function at 0. So imagine cutting it at 0, at pi, and at 2 pi. Okay, well, I've got to make those little red marks go away because it makes it look like I put zeros there. But you imagine slicing it, cutting the graph at those points. Okay, let me get rid of those little red marks. Then take the graph of the sine function between 0 and pi, the curve that arc that opens downward, and hold it fixed at y equals 1 and flip it upside down. Flip it upside down. If you flipped it upside down, it would look like this. But don't just flip it upside down. Flip it upside down and stretch it in an asymptotic behavior. So flip it upside down and stretch it up toward its vertical asymptote. Do the same thing on the other side. And let me see, I do a little better here. Pretty about the same. Okay, and that's a portion of one period of the cosecant function. Then do the same thing with this portion of the sine. Now we cut it here, we cut it here. So take this little portion right here and flip it upside down, holding it fixed at, holding the y value at -1 fixed. Okay, so holding the point at -1 fixed and -1 fixed, and flip that arc down and stretch it out. And what you're seeing is exactly one period of the cosecant function. It's a strange looking graph, very strange looking graph. Okay, those two arcs, that one that goes up and that one that goes down, they make up one period of the cosecant function. Okay. Finally, for the graph of the secant function, we use the same procedure. So secant is 1 over cosine. And the cosine x equals 0 at x equals 1 pi over 2 and 3 pi over 2 within one period of its graph. Okay, so let's get the graph of the cosecant function. Let's see if I get a big enough graph here. Okay, so at x equals pi over 2, I'm going to have a vertical asymptote. So let's do this. So at pi over 2, I'm drawing a vertical asymptote. And also at 3 pi over 2, I'm drawing a vertical asymptote. Okay. Let me get rid of the ruler. So there's pi over 2, because the cosine is 0 there. Here's pi. The cosine of pi is -1, so we don't get a vertical asymptote there. Cosine of 3 pi over 2 is 0. So I'll extend the x-axis a little bit. Here's my y-axis. So I'm going to do the same thing I did. I use the same technique I did for graphing the secant. I'm going to graph what's in the denominator of secant as a kind of a dotted graph. So here's 1, and here's the cosine function. This should be pretty automatic for you by now, the graph of the cosine, especially with all your work you did with sines and cosines. Let's see here. And then it increases at 2 pi, it goes back up to 1. Okay. So we're going to do the same thing. We're going to do the same thing as we did with the sine. In the interval between 0 and pi over 2, take that arc that's bending down right there and cut it at pi over 2 and bend it up across y equals 1. Okay, so bend it up, cut it and bend it up above y equals 1, holding it fixed at y equals 1. Okay, do the same thing with the arc between pi over 2 and 3 pi over 2. Cut it at pi over 2 and 3 pi over 2, so it's, and then bend it downward and stretch out the graph so that it has a vertical asymptote. I'll clean that one up, vertical asymptote. I'll clean that one up over here. Yeah. There we are, that's better. That last piece that last piece in the interval x value goes from 3 pi over 2 to 2 pi. I'm going to take that last arc, this arc that's bending down like that. I'm going to flip it. I'm going to hold it fixed at y equals 1 and cut it at 3 pi over 2 and flip it up. So let's do that. So let's see, we'll get something like this. That's the graph of one period of the secant function. Now the thing is, the graphs of secant and cosecant are identical. And as soon as I flip back to the cosecant, you're going to think they're not identical. This one's got two cups. One opens up, one opens down. This one's got a half a cup. One opens up, but half a cup that opens up, full cup that opens down, and the other half of the cup that opens up again. Well, if you can extend the graph of the cosecant function to the left by pi over 2, you're going to get, using that flipping technique where cut it and flip, you're going to get this portion here. Okay, so that graph would be between negative pi over 2 and 0. So we have one cup up and one cup down, and a little portion of one that opens up. But that little portion that opens up can be erased because the period of the secant function is 2 pi. And the distance between negative pi over 2 and 3 pi over 2, that's 2 pi. That's one period. Okay? So it's kind of an odd period to graph. We're used to graphing the cosine between 0 and 2 pi. But one period lies between negative pi over 2 and 3 pi over 2. Or you could take that little piece of the arc that opens up, that extra piece that we graphed, and move it over to the other side of the graph. But don't include both if you're asked for one period. If you're asked for one period, then you give that. Or you move that last little arc from 3 pi over 2 to 2 pi, so it's between negative pi over 2 and 0. Okay. In any case, we now have the other four trig functions. We have the tangent. Increases as we go from left to right and lies between negative pi over 2 and pi over 2 as vertical asymptotes. We have the cotangent, which lies between 0 and pi and decreases as we move from left to right. The graph is going down. Then we have the two oddball functions, the cosecant between 0 and 2 pi, one cup up, one cup down. The first cup is hugging the y-axis, and we also have one cup up, one cup down, but it's shifted. It's like taking the graph of the cosecant, the one you're looking at now, and shifting it to the left by pi over 2. Okay. All right, so this ends this video segment. There's not a lot I want you to do with the remaining four trig functions. Most of the work you did with the trig functions was in graphing sinusoidal graphs, sines and cosines. And for that, we had phase shift and amplitude and period changes and even some vertical shifts. For the other trig functions, I just want you to memorize one period of each. Okay, so that's going to end our video segment, and I'm looking forward to talking with you all again very soon.